Okay, welcome back everyone. It's our goal to derive the wave equation for gravitational waves on the Schwarzschild background. This will be, well, for the odd modes, this will be the famous Recco-Wheeler equation. That's the only thing I will derive here. There's also something for the even modes. This is called the Cirilli equation, but I will not deal it here. And I've outlined last time the 5-step procedure in which we will approach the Recco-Wheeler equation. So we are on a spacetime G mu nu, which is a perturbation of the Schwarzschild spacetime. G bar mu nu is now the Schwarzschild spacetime plus a perturbation. And then we have expanded this perturbation in the way that we here separated the part where the indices takes, if this is a Schwarzschild matrix in standard coordinates, mu and nu takes the values t, r, theta, and phi, right? So the Schwarzschild metric is written in spherical polars. So the index mu takes the values r, t, theta, and phi, and we decompose this into the RT part. A and B takes the values R and T, sorry. And then we have the mixed part. I think I forgot this too, because I have to use the symmetrized tensor product. There I need a 2, right? The symmetrization involves a factor 1/2, so I need a 2 in order to fit with the left-hand side. This is A sigma dx sigma dxa. And then I have the purely angular part. So A and B takes the values R and T, and sigma takes the value, and also omega, or capital Greek indices, takes the value theta and phi. Yeah, these are the angular parts. So then we have H, say sigma omega dx sigma dx omega. So this is, I should have left a little bit more space, sorry. Plus H sigma omega dx sigma dx omega. So here we have a scalar function on the sphere. Here we have a one form, or a covector field, which is the same thing on the sphere. And here we have a tensor field, a second-rank tensor field on the sphere. And that's what we now have to expand into spherical harmonics. So we did this last time. I think everyone could easily follow when I developed or expanded the HAB in terms of spherical harmonics. These are just scalar functions. Everybody knows how to expand the scalar function into spherical harmonics. So we have written HAB in the form, that's the usual range of the indices m and l of the spherical harmonics. And the coefficients, I think I called them u. Did I call them u? Let me check. Should use the same letter. Yes, u. U, A, B, L, M, Y, L, M. Yeah, so, oops. So this is an expansion in terms of spherical harmonics. These are scalar functions. Maybe I should have written the arguments. That could be helpful. They depend on, T, R, theta, and phi on all coordinates. The coefficients depend on T and R only. And the Y, L, N, as everybody knows, of course, depend on the angular coordinates. So what was a little bit more advanced was the expansion of these things, of the covector and the tensor part. So we have written the H A sigma dx sigma. It's a covector field on the sphere for the values A equal T and A equal R. Right? So these are two functions on the sphere. L equals 0 to infinity, m equal minus L to L. And I've denoted the coefficients v hat and v. So here we have v hat, A, Lm which depend on T and R. And I've given you the basis vectors last time, CLM sigma of theta and phi. And well, these are covector fields, so I need, there are two linearly independent covector fields on the sphere, right? So I need two sets now. One basis set I denoted psi, and the other one I denoted phi, TR, phi, LM, sigma, theta phi, and dx sigma. I forgot the dx sigma. Oops. These are one forms on the sphere. Yes, fine. And I've given you these things last time explicitly. So they were given, this was given in terms of a derivative of the spherical harmonics. The covariant, or partial, it doesn't matter, it's the same thing. Derivative of the spherical harmonic is a covector field. And then we constructed this as orthogonal to this covector field. So these two things then give us a basis for each LM.
May I ask a question?
Sure.
So why did you choose exactly these spherical harmonics as a functions under the derivative?
Okay, you could choose any basis for scalar functions, covector functions, and tensor functions. Why it is convenient to choose the spherical harmonics? Because our differential operator, this thing satisfies a differential equation. Yeah, the linearized Einstein equation. This involves the wave operator. And we know how the wave operator acts on the YLM. That's why it is convenient. Yeah? You could choose any basis, yeah? But it's convenient to choose a basis for which you know how the operator acts on it. Yeah? This simplifies matter, of course. So it's really convenient to choose the spherical harmonics. Well, actually, whenever you have a problem of spherical symmetry, and you have an operator which involves the Laplace operator. Yeah, the wave operator has a temporal part, and the spatial part is just the Laplace operator. The Laplace operator acts on the spherical harmonics. The spherical harmonics are eigenfunctions of the Laplace operator. That's why it is convenient.
So its action actually is similar, irrespective of whether we have scalars or vectors or tensors?
Well, the difference is that if we have covectors or second-rank tensors, then we cannot use the spherical harmonics themselves because they are scalar functions. But it's a good idea to use something which is constructed out of the spherical harmonics. And that's what we did. We used the derivatives of the spherical harmonics. Yeah? First derivatives, these are just the first derivatives of the spherical harmonics. I had them on the board last time. And these are constructed in a way that they are orthogonal to these derivatives of the spherical harmonics. And what I write now, the basis for the second-rank tensor fields, there we began with a second derivative of the spherical harmonics, and then we completed this to a basis. So, as I said, you can choose any basis you like. The only condition is the things must be linearly independent. Everything which is linearly independent can be used for a basis. But if you make a stupid choice, then the equations will be even more difficult than they will become here. Yeah? This will be difficult enough, actually, as you will see in a minute. Okay, so this is the covector part. Now we come to the tensor part.
Well, I mean, my question here was, so it is also convenient not only for scalars but for the vectors to
yes.
use
Yes. Well, this thing here, or rather this thing, satisfies the differential equation, the linearized Einstein field equation on the Schwarzschild background. And this is a differential equation which involves the wave operator on the Schwarzschild spacetime, on a spherically symmetric static spacetime. And the wave operator on a spherically symmetric static spacetime involves the Laplace operator. So it's a good idea to use something which has something to do with the eigenfunctions of the Laplace operator, and that's the spherical harmonics. Yeah, the spherical harmonics are the eigenfunctions of the angular part of the wave operator. That's why it's convenient to use them. Okay, and then we have the purely angular part, the tensor part, dx sigma, dx omega. So this, I need three basis vectors, because the set of all second-rank tensor fields on the sphere is a three-dimensional vector space. Yeah? At each point, I have three independent second-ranked tensor fields, because a second-ranked tensor field on a symmetric second-ranked tensor field on a two-dimensional manifold has three independent components, right? The two diagonal elements and one in the off-diagonal, in the right-hand corner, upper right-hand corner. In the lower left-hand corner is then determined by symmetry. 1, 2, 3. So there's three independent things. And I've given you the basis last time. And I introduced some funny notation for these things. That's my private notation. It's not actually standard. So I use, what did I use? V hat, W hat, W tilde, and W. W hat, LM. TR, this was with the first set of basis vectors, LM, sigma, omega. These were just the second derivative of the spherical harmonics. And then we constructed two other basis sets which are linearly independent of this thing. VLM tilde, TR, I think I called it phi and chi. Yes, phi and chi. LM sigma omega theta phi to W TR chi LM sigma omega dx sigma dx omega. Okay, let's count these things. How many components do we have? So if I fix L and M, yeah, if I do this for a fixed L and M, then I have here how many functions. A and B takes the values T and R, right? It's TT, TR, and TT. RT is the same as TR because it's symmetric. So I have 3 times 1 from the scalar field. Yeah? These are scalar functions, and I have 3 scalar functions. Then here I have how many? These are A takes the value T and R. Here again, so I have 2 functions, and for each the value A takes 2 values, so I have 2 plus 2. And here I have 1, 2, 3 functions, but there's no dependence on T and R, so it is 1 plus 3. So let me calculate this. 3 plus 1, that's 3. That's 4, makes 7 altogether, makes 10. Okay. So I have altogether 10 independent components. And of course it fits. This is a symmetric second-rank tensor field on a 4-dimensional manifold. How many independent components does it have? 10. Yeah? So we have really done a good job. We have introduced just the right number of functions to express these vector fields. Okay, so now this was the second step, right? And there was the first step. It was just the first step. Now comes the second step. So I had outlined this 5-step procedure on last Friday. So the second step was that, well, that's rather complicated, right? We have a lot of functions, 10 functions altogether. That's too much for us. We don't want to deal with all of them. And the idea is we separate them into those which behave even under parity transformations and those which behave odd. And we consider only those which are odd under parity transformation. This gives us a Reggio-Wheeler equation. The other one would give us a Cirilli equation. So we consider only and that's what Reggio and Wheeler did in their famous 1957 paper. Consider only odd perturbations, perturbations that are odd with respect to parity transformations. So now we have to recall what is a parity transformation. It's something which is very important in particle physics. Yeah, if you if you classify elementary particles, you have the Lorentz group as the invariance group, and then one of the most important question is which functions behave odd and which functions behave even, which functions are even under parity transformation. What's a parity transformation? Parity transformation is just the spatial inversion. Yeah? Spatial inversion means I have my three-dimensional space parameterized with position vectors r, and now I invert each vector r. So I replace r by minus r. That's what is called a parity transformation. Yeah, the spatial inversion. So what is the parity transformation in terms of our angles theta? So the angle theta goes to pi minus theta. That's a reflection at the equatorial plane. Yeah, theta comes down from the positive z-axis. And if I want to invert the vector, then I have to replace theta by pi minus theta. And the phi is to replace by phi plus pi. Yeah? So I first reflect at the equatorial plane, and then I rotate by 180 degrees. Both things together give me a spatial inversion. So that's a transformation. And now we have to see how behave our basis vectors, all these animals here. The YLM, the psi, the phi, the psi, the phi, the chi, how do they behave under this transformation? And you will see that all of these basis vectors transform either evenly or oddly. So what do we mean by that? By definition, an odd, or let's begin with an even. An even transformation behavior is the following, that if I have a function, it will usually depend on these indices FLM. You see all these basis vectors depend on the indices FLM. And of course, they are functions on the sphere. This means on theta and phi. So if we have that this goes into minus 1 to the power of L. Sorry, the transformed thing, of course. So this means pi minus theta phi plus pi. Yeah? So I have a function FLM, which depends on theta and phi. So I ask, how is this function behaved at the transformed values, where I just invert the position vector. And if this comes with a factor minus L1 to L, FLM theta phi, then I call it an even transformation. Well, what's the idea? If L is even, then this is just the 1. This means if L is even, then this thing is invariant under parity transformation. Yeah? So being invariant under even, transforming even with respect to parity transformations means being unchanged if I transform with if my index L is even. Yeah? And an odd transformation. Yeah, that's now easy to guess. It's the same thing with the other sign. FLM pi minus theta phi plus phi is minus 1 L plus 1 FLM. Yeah, this means if L is odd, then this is just the factor 1, then this doesn't change. Yeah? So this means nothing changes if L is even. This means nothing changes if L is odd. And it's easy to see that if you have any functions, you can always decompose this in a part which transforms evenly and a part which transforms oddly. So these are, if you talk about basis vector fields, and if we have chosen the basis appropriately, then we can distinguish between even and odd. And now we have to check for all of our basis vector fields, for this, for this, for this, for this, for this, for this. Are they even or are they odd? And I will not do this on the board. I will do it just for one. But I will write the result on so we find, my claim is that YLM theta phi is even. And I will prove this in a minute. And for the other basis vectors, I will just write it down. So phi ALM, LM sigma, of course. These things depend on the angular parts, yeah, LM sigma. The phi's, these were the derivatives of the, as a covariant derivatives. This is odd, right? No, it's even. The psi, the other ones, which are orthogonal to the phi's. This is odd. And then we have the three basis vectors for the tensor perturbations. Phi, I interchanged this. The phi's are the covariant derivatives, and they are even. And these are the things which are orthogonal to the psi's, and they are odd. Yes, that is correct. And then I have the psi's, LM sigma omega. Oops. This is the psi's is even. This is a covariant derivative. The second covariant derivative now of the y's. The phi's. This was just symmetric up to a normalization factor. And this is also even. And the last ones, the psi, they are odd again. You see, if you count this, you see that there are much more basis vectors which are even than those which are odd. And that's the reason why it's much easier to treat the odd perturbations. Yeah? That's the reason why we restrict to the odd ones. Okay, as I said, I will not prove this for all of them. I've typed it out here carefully, and I hope it's correct. And but what I want to prove is just the first thing, for the YLM themselves, that they are even, so that you see how the procedure is done. LM theta phi is even. That's what I want to prove. So what are the y's? Remember? There are some normalization factors, which are, of course, completely irrelevant. They depend neither on theta or on phi, so they play no role whatsoever. Then we have the associated Legendre polynomials. And then we have the e to the I m phi. Yeah? So here's the index L, the angular momentum quantum number. And here we have this magnetic quantum number, m. And now we have to recall what is PLM. PLM of an argument x, that's a real number. In our case, it's cosine of theta. PLM is, here I have it, -1 to the m, 1 minus x squared m half, d by dx to the power m, PLX. And the PLX are the Legendre polynomials. These are the so-called associated Legendre polynomials. These are the Legendre polynomials. PL of x is, what's the normalization factor? 1 over 2L factorial. d by dx to the power L x squared minus 1 to the power L. So that's a polynomial, right? If you work out this derivative for any L, you always get a polynomial. Yeah, so it's a Legendre polynomial. Okay, so we have to see how do they transform if I change theta into pi minus theta and phi into phi plus phi. So phi LM, theta, no, pi minus theta, phi plus pi is what? This is this normalization factor which plays no role. PLM of cosine theta, PLM of pi minus cosine theta is minus cosine theta, right? And if I replace phi by phi plus pi, then I get e to the im phi plus pi in the exponent. And I have to compare this with YLM at the original position, theta and phi. And the claim is that I just get a factor minus 1 to the power L. So let's see. PLM, okay, I have to do it step by step. PL of minus x, what is that? PL of minus x, let's look at this equation here. 1 over 2L, L factorial. Here I have, if I replace x by minus x, I get the minus x to the power L. Minus 1 to the power L, sorry. And here it doesn't matter, yeah, because it's a square. The square of x is the same as the square of minus x. So it's x squared minus 1 to the power L. So if I now compare this with PL of x, then I see that the only difference is this term, minus 1 to the power L. So this is minus 1 to the L, PL of plus x. Yeah? And this means that PLM of minus x is this here, is minus 1 to the m. And here, if I replace x by minus x, nothing changes because it's squared, 1 minus x squared. And half. Here I get wait a minute, a minus 1 to the m. Yes, exactly. Here I get a minus 1 to the m. d by dx to the m. And then PL of minus x is, as I have derived here, minus L to the L PLX. Okay? And you see this very conveniently drops out. This is, of course, a constant. I can pull it out. So this is minus 1 to the L. 1 minus x squared m half PLX, d by dx to the m PLX. And this is what? This is, oops. Yeah, there's a factor. Oh, maybe I shouldn't have cancelled this. Yeah, because I need one factor minus 1 to the m for the PLM. So one factor survives. Then I have this factor here, minus 1 to the L, and then I have PLM of x. Okay. And this means now I can collect everything together. Pi minus theta phi plus pi. I've written it here. It's what? So it's CLM. Oops, where is it? Here it is in the first line here. So CLM. PLM of the negative argument, that's what I've calculated here. That's minus 1 to the L, minus 1 to the L, PLM cosine theta. And that's the PLM, and then the EM, e to the IM phi. And what is this here? E to the IM pi. This is minus, e to the I pi is minus 1, right? So this is minus 1 to the m. Yeah? E to the I m pi is e to the I pi to the m. and e to the I pi is -1. So it is this here. And now it goes away. Sorry, I anticipated this. Should have done it only here. And now you see, if I take this factor out of everything, then what is left is just the YLM, theta and phi. And this was my claim. Yeah? So if I make a parity transformation, if I replace theta by pi minus theta and phi by phi plus pi, I get the same spherical harmonic function with a factor -1 to the L. And that's what we mean when we say the YLM transform evenly. And in the same thing, you do it for the derivatives. It's more involved for the derivatives, of course. So actually, well, I should make a remark on this. We have defined these things, these basis vectors, in terms of covariant derivatives. If you want to work them out, in particular the second covariant derivative, which cannot be directly replaced by the partial derivatives, then we need the Christoffel symbols, of the Schwarzschild metric. Yeah, the covariant derivative is a partial derivative plus a Christoffel symbol term. So we really have to insert the terms as the Christoffel symbols of the metric. And this makes the calculation of the transformation behavior of these things a little bit awkward. So it goes over 2 sides or so, 2 pages in this script here. But in principle, it's exactly like what we have done here. So you can do this for all these things. And then we know if we say, okay, we restrict to the odd perturbations, then we have only these 2 sets of basis vectors. Here, these phi Lm sigma and the chi Lm sigma omega. So we have no scalar perturbations. We have only one set of vector perturbations, and we have only one set of tensor perturbations. Well, you can do the same story, exactly the same thing. First, in quantum mechanics. In quantum mechanics, you have a wave function, phi or psi or whatever you call it. It's a scalar function. So in this case, you have only the first term. And you expand in terms of YLM. That's what's done in every course on quantum mechanics if you deal with spherically symmetric problems. Yeah? And you get these things, and you have only even perturbations. Nobody mentions this usually in this context because there are no other perturbations than the even ones. Yeah? You could also do it in electrodynamics. In electrodynamics, you usually use the vector potential. That's convenient as a variable. The vector potential is a thing with one index. So you have these 2 things here, if you expand the vector potential. And you see there are perturbations which are even and perturbations which are odd. If you expand the vector potential into spherical harmonics. And if you write this out in terms of the electric field and the magnetic field, then you will see that the electric field is associated with the even perturbations, and the magnetic field is associated with the odd perturbations. Yeah, the transformation of the electric field is that it is even under parity transformations. It's a polar vector, as one says. And the magnetic field transforms oddly under parity transformations. Yeah, it's an axial vector, as one says. So here we are now in a more complicated situation. We have the scalar things, which we know from the wave function in quantum mechanics. We have the vector things, which we know from electrodynamics. And in addition, we also have the tensor parts. Yeah? So it's considerably more complicated. But it's doable. And actually, Retcher and Wheeler did it in 57, at least for the even perturbations. Okay, so this was the second step. So we know now to which perturbations we have to restrict. Maybe I should write this down. So which perturbations do we have now? We have the odd perturbations. How many coefficients do we have? Maybe it's helpful to calculate this. So our general perturbation was this here, P, R, theta and phi, dx mu, where the scalar part is gone. The odd part of the vector part is sum L equals 0 to infinity, M equal minus L to L. This is the V without a head. Yeah, the V without a head. how did I call this? Oops. Yes, exactly. VALM. TR. These were the phi's. Yeah? The phi's were the things which are orthogonal to the covariant derivatives. Phi LM sigma dx sigma, and I have to sum over dxa. And then I have from the tensor parts also only one set of perturbations, the w's, the thing without heads or tildes. These are the ones which are odd under L, M, sigma, omega. Yes. Oops. TR, dx sigma, dx omega. That's it. So that's the kind of perturbation we are dealing with now. So for each LM, we have two V's. Yeah, A takes the value T and R, and we have one W, 3 functions. It's still too much, right? Remember, how many degrees of freedom does a gravitational wave have? Remember how many polarizations? Well, we calculated on flat space first. Of course, in principle, it could be possible that it changes on curved space, but I just tell you that it's the same thing on curved space. So how many degrees of freedom do we have? We will see it in a minute, that we have the same number of degrees of freedom. How many degrees of freedom? How many polarization states? 2, exactly. Yeah, so we have we have here 3 functions. These are 2, this is 1. So we still have a gauge freedom, of course. We haven't used any gauge condition until now. Yeah? We haven't talked about gauging in this context at all. So we have the complete gauge freedom. So we expect that of these 3 functions, we can kill 1 by gauge, by fixing the gauge. And actually what Redscher and Wheeler did was they killed the W. And then they were left only with the 2 functions VTLM and VRLM. Yeah? And they are invariant properties of the gravitational wave. They gauge invariant properties. They cannot be gauged away. So we will now use the gauge freedom in order to kill the W's. You could kill some other combination. Yeah? So there's, of course, always a gauge freedom. A freedom how you choose your gauge. But I follow Redscher and Wheeler, and they killed the W's and left the VT and VR. So this is now step 3, right? So step 3 is use the gauge freedom. To kill W, these things here, WLM. And now comes a very subtle point, actually. This was when I came across this derivation for the first time, a couple of years ago. Actually, I was puzzled by this for quite some time, and it took me some time to understand this, because you do this gauging for a fixed LM. Yeah? We fix L and M now. And I tell you how we do the gauge, by which gauge transformations we reach the goal of killing the W, and he will see that the gauge function depends on L and M. And we have to discuss what this means. Yeah? So when I heard about this, I thought, wait a minute, this is nonsense. Yeah, you should introduce a gauge condition which is the same for all L and M. But actually, that's not necessary. Oh, everything works. Wheeler and Redscher, they knew what they were doing. It's everything correct. But it's a subtle point. So what we do is now fix L and M. So make a gauge transformation. Well, remember, what is a gauge transformation? It was a coordinate transformation of this form, where we assume that this thing is smaller first order, so that everything can be linearized with respect to this thing and its first derivative. And we calculated already how the h mu nu change under such a transformation. They change by the covariant derivative of the f, symmetrized. Yeah, that's what we calculated last week, I think last Monday. That if you do such a gauge transform, we are now back to the original, to the quite general formalism. Yeah? No Hilbert gauge, no restriction of the gauge whatsoever. We work with a quite general transformation. We do this ansatz with an arbitrary h mu nu. Then we have the full gauge freedom. This means we have the freedom of making transformations of this form, and this transforms the h in this way. And now the question is, can we choose this for a fixed Lm to kill the WLM? And the answer is yes, and I will prove this. Okay. Oops. Yes. Choose f mu such that the following holds. So the index mu takes the values 2, t, r, theta, and phi. Yeah, it takes the values a, which stands for t and r, and sigma, which stands for theta and phi. And I choose them in such a way that the fa is 0. Yeah? If the index is t or r, then it is 0. And the f sigma is what? The f sigma is, well, this depends, of course, on all coordinates. Maybe I should write this. Fa, tr, theta, and phi is 0. And we have f sigma. This means f theta and f phi. Tr, theta, and phi. I make an ansatz for this. I make an ansatz that this is a function lambda Lm. The gauge will depend on L and M. Yeah? So the gauge function will involve the indices L and M, T of R, times our basis vector field, which I called, how did I call it? Phi. So this phi was epsilon, the Levi-Civita symbol, the totally antisymmetric second rank tensor field on the sphere, which is a function of theta and phi. Covariant derivative. Let me write the argument later. Let me put a bracket here. Covariant derivative omega YLM. Theta and phi. Yeah? So these things, these were the psi omega LM. And then I applied this antisymmetric animal here. Then I get something which is orthogonal to this, and this was what I called phi. Yeah, this is a phi. And my ansatz now for the gauge transformation is I take this basis element and multiply it with a function lambda of L and M, which I will determine now in such a way that the omegas go away. And my claim is that this is possible, and I have to prove this. So what is the transformation of the H? Then the H, here, the H mu nu. Well, first let me do the HAB. TR, theta, and phi. So this is HAB plus, no, this transforms into, this transforms into HAB. Okay, I dropped the arguments, otherwise I have to write it in every term. It's a little bit awkward. HAB plus del A FB plus del V FA. Yeah, question to the audience. We have assumed that the FAs are 0. Does this mean that these two terms are 0? One of my favorite examination questions. Okay, if this here is 0, if FB is 0, is then the covariant derivative of this also 0?
It's equivalent to 0.
What do you mean by equivalent?
At every point.
Well, this is 0 at every point. FB is 0 at every point. It's identically 0.
Then this is also 0.
Okay, Pavel says it's always 0.
It also has like this, Christopher symbol.
Yes, okay. He corrected himself. There's a Christopher symbol, yeah? Let me write this out. What does this mean? It means this is dA fb partial derivative. This is of course 0 if this is 0. If you have a function which is identically 0 and you differentiate them, then it's also 0. But then you have this additional term, which is, okay, it's the del bar, so I have the gamma bar here, right? Gamma bar mu f mu plus, plus d bfa minus gamma bar ba mu f mu. Okay, so this here is 0, obviously. This here is 0. But now we have to look at our Schwarzschild metric. We have to see if these Christoffel symbols are all 0. Well, mu takes all values, t, r, theta, phi. Well, if this mu is t or r, then this is 0. Yeah? But what about the other ones? So I have this is HAB minus gamma bar. If this is a theta or a phi, this means a sigma. I have to see what is this. This is not 0. Yeah? So in principle, this could be different from 0. Minus gamma bar sigma BA F sigma. But if you look at the Christoffel symbols of the, this is of course 2 times the same thing, right? So I can write this as HAB minus 2 times gamma sigma AB F sigma. So these are not 0. The F sigmas, here they are written. Yeah, they are not 0. Where are they? Here. They are not 0. But now you have to check if the sigma takes the value theta or phi. If the upper indices of the Christoffel symbols are theta and phi, and the lower indices are r and t, do we have non-zero Christoffel symbols? And if you check with the Schwarzschild metric, you see that all of them are 0, actually. Yeah? So you really need the Christoffel symbols of the Schwarzschild metric. I've typed them out here, but I'm too lazy to put them on the board. So you can just check later. So the HAB doesn't transform. Yeah, the HAB, if A and B takes the values T and R, is invariant. So this is just HAB. So the interesting thing is what happens to the H sigma omega if the index takes the value theta or phi. And then we get something, of course. Otherwise, the whole ansatz would be rather stupid. And I will tell you what we get. And for that, we will need the property that the covariant derivative of the epsilon symbol, the Levi-Civita tensor, that this is 0. Well, this is generally true. If you have a metric on a manifold, here the manifold is a two-dimensional sphere. Yeah, if you have a metric on a manifold, you introduce the volume element associated with this. That's what we call the Levi-Civita tensor field. Then this is always covariantly constant. So you can check this quite generally, but you can also check it for our specific expression for the epsilon, which I gave you last time. So I've written the epsilon last time explicitly on the board. And if you calculate the covariant derivatives with the help of the gammas of the Schwarzschild metric, you can verify that they are 0. And as I said, that's a general result. If you have verified this once for a particular metric, then you can take it for granted for every other metric. Okay, so we calculate, I think that's not enough space. Let me do it here. So the H sigma omega is what? Yes. Okay, so this transforms into HAB plus lambda. I call this lambda, this function, which is a function of t and r, chi lm, sigma omega, theta and I didn't write the arguments. Okay, so I write them never. And sorry, that's nonsense, of course. That's what I mean, yes. Okay, let me check what I will actually do on the board. Okay, should I write this out? Okay, let me do it in a different way. Oops. So unfortunately, a lot of calculations, and I try to minimize the work which I do on the board. So let me see. Yeah, okay. So my claim is that the covariant derivative of the epsilon is 0. Okay, let me verify this. So the covariant derivative is what? It is the partial derivative minus, right? Yes, minus gamma bar. What else do we have for indices? What Greek letters are still left? Let's say, I don't know, pi, capital pi. Sigma omega, epsilon, sigma delta, minus gamma bar pi, sigma delta, epsilon, sigma delta, pi omega, sorry, this is wrong here. Pi delta, omega pi, that's it. And now we have to recall what the epsilon was. Or rather, no, we just have to recall that it is, we distinguish two cases. For omega equal to delta, well, then this is 0, of course, because this is antisymmetric. So I have 0 is, let me see. Yes, this is antisymmetric, right? So if I insert the same index for both things, then it's the same thing. And here I get the same expressions, but the indices at the epsilons are interchanged. Here the pi is the first index, here the pi is the second index, but epsilon is antisymmetric. So if omega is the same as delta, then I get here's a negative term and here's a positive term, which cancel each other. So I get that del bar sigma epsilon omega delta is 0 if the two indices are equal, right? This term is 0, and these two terms kill each other because they give the same thing because of the antisymmetry of the epsilon. So I only have to consider the case that omega is unequal of theta. It's not the same as delta. But how many indices do we have? How many possibilities for omega and delta we have? Only two, theta and phi. Yeah? So if they are not equal, then one must be theta and the other one must be phi. So we must have, so if we have for omega not equal delta, we have just to consider the case that it's the derivative of omega theta phi. That's the only thing we have to consider. And this is what? So this is, yeah, I have to write this out actually. So this is, oops. This is delta sigma epsilon theta phi. And then I have minus, yes, minus gamma bar. Now I have to be careful. Sigma theta omega epsilon omega phi minus gamma bar sigma phi omega epsilon theta omega. And now we have to check again these values for the gammas. So if this takes the values theta and phi, and here the same thing, if omega and sigma takes the values theta and phi, then actually we find that this is 0. Yeah, we have to insert the gammas from the Schwarzschild metric. We have to look them up. And the same thing, I've written these things down last time. The epsilon, theta, and phi were given last time. Also, the partial derivative is, let me see. No, sorry, this is wrong what I've said. Sorry. Slowly. So let me do this. I have to do it separately, sorry. So nabla bar theta, epsilon, theta, phi is the following. This is the theta, epsilon, theta, phi, minus gamma bar, theta, omega, epsilon, omega, phi, minus gamma bar, omega, theta, phi, epsilon, theta, omega. Okay, the epsilon, theta, phi is r squared sine theta. That's what I've given you last time. This you have to look up, and this is 0. Yeah, this is 0. And this thing here, okay, you have to split it. It is actually non-zero for one of the two indices. Namely, if the index, of course, if the index is theta, then I give a 0 here because it's antisymmetric. So I can get something only if this is phi. And this is non-zero, actually. This Christoffel symbol you have to calculate. It is r squared cosine theta. Yeah? So you look up the Christoffel symbol for the Schwarzschild metric. But if you now compare these two terms, derivative of sine theta is cosine theta, and the two terms cancel, and you get 0. And analogously, you get it for the covariant derivative with respect to phi. This is d theta epsilon theta phi minus gamma. Here I have what? Phi theta epsilon theta. Then this must be a phi, right? Minus gamma bar phi. Here I have the first index, no, the second index phi. What did I do? Phi theta. This is wrong here, sorry. Phi theta. Then the theta is replaced. Here I have a phi and here I have a theta. Okay, that's it. You see? Phi theta, phi theta. The phi is retained, and then this must be theta. Otherwise it would be 0. If this would also be a phi, it would be 0. And gamma phi, epsilon theta, and the summation index, which must be a phi. Okay, and what is this? You have to check this again. This is r squared sine theta. So if I take the derivative with respect to phi, I get 0, and all these things are also 0. So I get a 0 altogether. Yeah. So it is a down-to-earth check of the fact that this is actually 0. Yeah, but if you realize that this is a Levi-Civita tensor field on the sphere, you can just deduce this from a general result that the Levi-Civita tensor field is always covariantly constant. But if you are not familiar with this fact, you can just check it in this way. Okay, so this is 0. Then we have to calculate what? So we have that our H sigma omega transforms into H sigma omega plus the covariant derivatives of our functions f. And the f, we know what it is. The H sigma omega is W Lm chi Lm sigma omega plus the transformed thing. Okay, what was this? The f omega, it's somewhere up there. Here it is. Here it is. This expression. I insert this expression now. Lambda Lm epsilon, have to be careful with the indices. What are the indices? The indices is an omega down. So I need a new index, say pi, del bar pi YLM. Everything under the derivative plus del bar omega lambda Lm. So the index down is a sigma pi del bar pi YLM. Okay? Yes. So this is what? It's WLM chi Lm sigma omega. And now use the fact that these things are covariantly constant. So I can pull them out of the derivative. Epsilon omega pi. Yeah, the derivative of acting on this gives 0. So I just have to calculate the derivative of these two terms. So I get lambda Lm del bar sigma del pi YLM plus the term where this acts on the lambda. Lambda Lm del par YLM. Let me see. The lambda Lm, wait a minute. The lambda Lm depend only on t and r. And if you, these are scalar functions with respect to the angular coordinates. So I could pull them also out of the bracket, right? So this is nonsense what I've written here. Well, it's not nonsense, but I've added a term which is actually 0. So the derivative, as I said, the derivative on the epsilon gives a 0, but also the derivatives on the lambda gives a 0. Why? Because the lambda depends only on t and r. It's a scalar function, with respect to the angular coordinates. A scalar function covariantly differentiated is the same as partially differentiated, and a partial differentiation with respect to theta and phi gives a 0. So this is nothing. And here the same thing. So here I have epsilon sigma omega lambda Lm del bar omega del bar pi YLM. That's it. And now we have to recall what the chi's were. What the chi's were. And actually the chi's were exactly these expressions. Yeah, the second derivatives and then transvected with the epsilon, yeah, to make it orthogonal to the second derivative. These were the psi's. The second derivatives were the psi's. And the chi's are the things which are transvected, these things with the epsilon. So what I have here is just, is it plus or minus? It's plus WLM plus lambda LM, the chi. Yeah? So you have to look up how we defined the chi last time. The chi's were defined exactly as a term without the lambda LM here. Yeah? These two terms without the lambda LM. Here we take the second derivative and we transvect with the epsilon to make it orthogonal to the second derivative. And that's the transformation behavior of the H sigma omega. And now it's, yeah, it's obvious what we do. We want to kill these terms. So we choose the lambda LM in such a way that they kill our old W's, so the new W's are 0. So we choose lambda LM. They are functions of T and R. These are our gauge functions. We can choose them arbitrarily as minus WLM, which are also functions of T and R. Yeah? And then the H sigma omega, yeah, the angular parts, the tensorial part on the sphere is transformed to 0. And that's what we wanted to do. So our perturbation is then a purely covectorial perturbation. So we have H mu nu dx mu dx nu, which in the beginning had a scalar part, a covector part, and a tensorial part. We got rid of the scalar part because we restricted to odd perturbations. We restricted the covector part to 1/2 of the sets by choosing odd perturbations, and we killed all of the tensorial parts by assuming odd perturbations and choosing the gauge appropriately. So this is now for a particular LM. I think I've written somewhere here, fix L and M. For a fix L and M, this is just VA LM TFR, and this was called phi, right? Yes, phi. Phi LM sigma omega dx sigma dx omega. Is that true? No, sorry. I have to sum over the A, of course. Nonsense. dxa. Yeah, the A must be summed away, of course. So we end up with 2 degrees of freedom. So we have 2 degrees of freedom for our gravitational waves, namely the function Vt Lm of T and R and Vr Lm. And we have no gauge freedom anymore. We have now fixed the gauge completely, right? Remember when we introduced the Hilbert gauge, this was a differential condition. This still left the condition, the possibility to choose the f if it satisfies a certain differential equation. Here it's different. We really fixed the f, not the derivative of f. Really the f itself was fixed. Yeah? So that we have no gauge freedom left. Yeah, and the equations in this gauge, which we have chosen, where the w's are killed, where we have just this expression, only these 2 vectorial perturbations or covectorial perturbations left. This is called the Recce-Wheeler gauge, because it was used in this famous 1957 paper by Tullio Recce and John Wheeler. Okay, so this was the preparation. Now begins the hard work. Yeah, it's really true. The hardest work now begins. We have just transformed our variables in an appropriate way. We haven't talked about the differential equations yet, which we have to solve, right? Einstein's equation was not yet in the game. Now we have to plug this ansatz into Einstein's field equation, and we have to solve it. And that's, of course, the hardest part of the work. And I will not do it on the board, but I will tell you as a general procedure. So the goal is now to get a differential equation for these two functions, VTLM and VRLM. Yeah, these two functions are to be determined. And please keep in mind, we do this for a fixed L and a fixed M. At the moment, we have L and M fixed, because the gauge was chosen, adapted to a particular choice of L and M. So this should now be step 4, I think. So step 4 is, plug this ansatz into Einstein's field equation. And by Einstein's field equation, of course, I mean the linearized field equation. The linearized field equation around Schwarzschild spacetime in an unspecified gauge. Yeah, remember, we first derived this field equation without talking about the gauge freedom. And then, for what I did last week, it was convenient to use the Hilbert gauge. We are not yet in the this time we are not in the Hilbert gauge. Yeah, actually, you can check if with these assumptions we have made here, you can check is now the Hilbert gauge satisfied or is it not, and you will find in general it is not. Yeah, so the Rätsel-Wheeler gauge is a different gauge than the Hilbert gauge. Actually, it satisfies the trace-free condition. That's not difficult to show. So you see that you can check that in the Rätsel-Wheeler gauge, the trace of H is always 0. So the H is the same as the gamma. Yeah, this trace reverse quantity is the same as the H. Gamma mu nu is the same as H mu nu. But the covariant divergence of H is not 0 in general. So it's not the Hilbert gauge. So you are not allowed to use the equations which we have derived in the Hilbert gauge. You have to be careful with this. So how does the field equation look like? Actually, we derived it in an arbitrary form. So step 4, insert this expression which we had derived here in this last step, this expression here. Insert this expression into the linearized vacuum field equation. Actually, I had written this earlier in the form. This was a background Ricci, which in our case is 0. Yeah, because we are on Schwarzschild spacetime, which is Ricci flat, plus a delta R mu nu. And I had calculated this. I had really written this out in terms of the H's. Yeah? So we need this expression for the H's. We have to insert this, and then we get, how many equations do we get? Basically it's 10 equations, right? Mu and nu take on 4 values. A 4x4 matrix, which is symmetric, has 10 independent components. 4 in the diagonal and 6 in the upper right-hand corner. And we have a fairly high symmetry, we have spherical symmetry, and we have staticity. So you might have some hope that not all of the 10 equations are independent. And actually they are not, there are only 3 independent equations. Yeah? So this gives, after a long calculation, which I will not do on the board, this gives 3 independent equations. And I will write them down now and discuss. So what do we need for these equations? If you remember how these expressions looked like, they involve covariant derivatives and they involve the gammas. So you need to know the gammas on the Schwarzschild spacetime. And our basis vector fields involve these things. These things here. They involve spherical harmonics. So we need 2 things. We need to know 2 things. We need to know the Christoffel symbols of the Schwarzschild metric. We really have to insert them in the terms. And we also need to know how our differential operator acts on the spherical harmonics. So we need the eigenvalue equations for the gamma Lm, which you know from quantum mechanics. Yeah, L squared, the angular part of the Laplace operator applied to YLM gives L times L plus 1 times the YLM. Yeah, this famous eigenvalue equation of the angular momentum operator. That's what we also use. And then we get 3 equations, which I write down now. And these we have to solve. So it's not 10 equations. It's in this respect, it's not quite as bad as it could have been, but it's bad enough actually. So, okay, this goes over 1, 2, 3, 4 pages. And then comes the following result. So components which are non-zero are the T sigma component. Yes, this is non-zero. Yeah, if these indices are T and sigma, this gives something where the sigma takes the value theta and phi. And for these two cases, it gives the same equation. Yeah, so the T phi equation gives the same equation as the T theta equation. And it reads like that. It's 0, this 0. And on the right-hand side, we get what? 1/2 1 minus Rs over R dr dt VRLM minus dr dTLM plus 1 minus R over Rs. That's actually the worst of the 3 equations. The first one, dt VRLM over R plus L times L plus 1. This comes from the eigenvalue equations of the YLM, right? This is famous L times L plus 1 factor. VTLM 2R squared minus RS VTLM R cubed. And let me call this F1. F for field equation, that's the first non-trivial component. Then we have the R sigma component. Same thing. If you insert theta and if you insert phi, you get the same equation. Yeah? And it looks like that. It's a bit shorter than the other one, fortunately.
Sorry, but is it right that RS is once in denominator and once in numerator?
Let me check, but I think so. Oops. No, I think that's wrong. Sorry. No, it's the other way around here. Oops. RS over R, RS over R. Thank you. You had the right instinct. Yes. So the second equation, minus dt dr, VTLM, minus dt squared VRLM, minus 2 over R dt VTLM, divided by 2c squared 1 minus R over Rs. I think this time it's correct. At least that's what I've written here. Or is it again a misprint? No, I think it's again a misprint. I think it's again this here. Yes, I think so. I think so. Plus L times L plus 1 minus 2 VRLM divided by 2R squared. And that's a second, non-trivial component of the field equations. And then we have the sigma omega component. These are actually 4 components, right? TT, RR, theta theta, phi phi, theta phi, and phi theta. But all 4 components give the same equation. And this is, it's the following. It is 0 dr 1 minus Rs over R VRLM minus dt vtlm c squared 1 minus rs over r. This is F3. Okay, now let's have a look at these equations. So of course it's a set of partial differential equations for our two unknown functions vtlm and vrlm. Yeah, these are the coefficients of the unknown function. Of course, what you want to do is you want to decouple them so that you get a differential equation for only one of these two functions. And well, if you play around a little bit with the equations, you see that it's a good idea to introduce, or rather to substitute. All these things are functions of t and r, right? These are functions of t and r. Yeah, the angular parts are split off with the help of the spherical harmonics. So we introduce a substitution. So we introduce a new function QLM, which is 1 minus, I have again R over RS. That's not true, RS over R. I always made this misprint, I guess. VRLM over R. And then we can see that, let me see. Then F3 becomes simpler. So we insert this into F3. We can solve for d by dt of VTLM. It is what? Let's keep the 1 over c squared. But let's multiply everything with 1 minus rs over r. Here's a minus sign, so this becomes plus. And then I have d by dr of this expression, d by dr, of 1 minus rs over r times v. 1 minus rs over r times v is r times q with our substitution. Okay? And I think that's what I can calculate this. Let me calculate the partial derivatives here. This gives 1 minus rs over r. If I differentiate the r, I get a QLM. And if I keep the r and differentiate this, I get this here. Okay? Yes. Okay. This is 1 minus r QLM minus rs. Yes, fine. So this is what I call F3 prime. It's still the same equation as F3. I've just introduced a new variable. So what's the idea? Now I have expressed the time derivative of Vt in terms of expressions which only involve this q. And now I look at F2. Here I have a time derivative of Vt. Here I have a time derivative of, no, is this a t? Vr. No, this is an r actually, but here I have a dt. Yes, here I have a dt. So I can replace these two terms with the help of this equation. Yeah, the derivative of Vt, the time derivative of Vt, which I have here and which I have here. I can replace them, and then I have I get rid of the VTLM altogether. Then I have an equation for VRLM, which is the same as QLM alone. So I have decoupled the system. If I insert this into F2, so let's do this. Here's F2, so I have a 0. 0 is, okay, 2c squared 1 minus rs over r. So that's the r derivative of dt VTLM. It's the r derivative of dt VTLM. This is c squared times the right-hand side. And there was a minus sign, right? Here was a minus sign. Yes. Actually, the minus sign is in front of the entire expression. Yeah? So I have to be careful with this. So I have a minus sign here, dr c squared 1 minus rs over r QLM plus R dr QLM. That's the first term. The second term I just copy. It's a plus second derivative VRLM. And the last term, minus times minus, is plus 2 over R. Plus 2 over R, first time derivative of V. This is this here. This is C squared 1 minus RS over R, QLM plus R, oh my goodness, dr QLM. Okay, so this is the first expression. It is this term here, right? And the rest I copy, plus L plus 1 minus 2, VRLM, divided by 2R squared. So you see that now I can express everything in terms of the Q, because the VR is here. The VR can be expressed in terms of Q as well. So this is 0 minus dr. Let me do the following here. Let me write c squared over c squared, which is a 1. And then I can cancel this c squared. Okay? So then I have minus d by dr 1 minus rs over r, QLM, plus r dr QLM, plus 1 over c squared dt squared VRLM. And VRLM is r times q divided by 1 minus rs over r. That looks funny. Have I done this correctly? Vt. Okay, let's see what we get. 2r 1 minus rs over r QLM plus r dr QLM. And the entire thing is to divide by 2, by 2 1 minus rs over r, 2 1 minus rs over r, 2 1 minus rs over r. The last thing is fine, but the other ones are not. Okay, let me see. And what do we get here? Plus L plus 1 minus 2. VRLM. VRLM is R times QLM divided by 1 minus rs over r. And I have an additional 2r squared. That's not good. That's not good. This should go away here. Let me see. What do I want to get? Okay, let me see. I'm already 2 minutes over time, sorry. Oops. Let me see if I get this equation straight. So this will actually become a partial differential equation for QLM alone. And that's what we call the time-dependent Retsch-Wheeler equation for this function. And then we will split off the time part, and then we will get the time-independent Retsch-Wheeler equation. But I'm afraid I don't get it because something doesn't seem to match. Let me see. So if I multiply, this is 1 minus Rs over R squared. I think that's what I have to do. Okay, what do I get? So I multiply with 1 minus Rs over R squared. Then I get minus 1/2. 1 minus Rs over R squared. No, I have 1 in the denominator, so I get it only to the power 1 d by dr. 1 minus Rs over R QLM plus R dr QLM. I have multiplied with the squared. This is under the time derivative. This is independent of time, so I can pull it out of the derivatives, and these two factors go away. So this is plus 1 over 2c squared. These two terms are cancelled, so it's dt squared. The r is independent of time, so it's the second time derivative of QLM. QLM. And here, oops, sorry, here I get again the factor of 2 cancels. It's 1 over r. 1 minus Rs over R, QLM plus R dr QLM. And one of the terms cancelled and one comes in addition, so I get plus 1 over 2r 1 minus Rs over R L times L plus 1 minus 2 QLM. Okay, so the last term is fine. Let me see. No, this is not true. This should go away. These terms with R times dr, they should go away, but they don't, right? So I'm afraid I have something messed up. Okay, I'm 5 minutes over time. I think I have to clarify this, and yeah, I tried to get this straight last time. So what we end up with is actually a differential equation, where we have where we have a kind of a wave operator applied to the QLM. But I think there's something wrong. These two terms should go away, but they definitely do not go away, right? They have the wrong prefactor, and they also come both with a plus sign, so this cannot be true. What I want to get is just the term with second time derivative, and the second, and this here with the second R derivative. Sorry for that. So I think I have to stop now. I try to clarify this, and we continue next Friday. Okay, see you then.